For homologous series of linear chain molecules, there could be a match or mismatch between the characteristic periodicity of the host structure and the characteristic length of the guest molecules. In this talk, I highlight the influence of commensurateness or incommensurateness on both adsorption and diffusion characteristics. For background information on the theory, I refer you to my paper published in Physical Chemistry, Chemical Physics 2017. Watch also the video entitled Entropic Separations of Mixtures on my YouTube channel. Let's consider the adsorption of n-alkanes with carbon numbers ranging from 1 to 7, C1, C2, C3, C4, C5, C6, and C7 in cobalt formate. The cobalt formate structure consists of 1D zigzag channels. One unit cell of cobalt formate contains a total of 4 distinct channel segments. 1 channel segment, 2 channel segment, 3 channel segment, 4 channel segment. If we look at the conformations of the linear chain molecules, we see that the length of a propane molecule, C3, is commensurate with the length of 1 channel segment. On the other hand, the adsorption of normal hexane requires 2 channel segments to accommodate a single NC6 molecule. The NC4 molecule can occupy 1 channel segment only at high pressures. At low pressures, the NC4 molecule is slightly longer than the length of 1 channel segment. The commensurateness or incommensurateness of the guest linear alkane and the host cobalt formate structure has important consequences for the adsorption and diffusion characteristics, as we shall observe in the following slide. The graph here in the top left-hand corner shows CBMC simulation data for the unitary isotherms for normal alkanes in cobalt formate at a temperature of 300 Kelvin. CBMC stands for configurational bias Monte Carlo simulations. The y-axis presents the data with units of molecules per unit cell. The x-axis is the bulk fluid phase fugacity in pascals. Let's look at methane, shown by the stars. This is methane. The diamonds are for ethane. Inverted yellow triangles, propane. Methane, ethane, and propane have a saturation capacity of 4 molecules per unit cell. Recall that 1 unit cell of cobalt formate contains 4 segments, and each segment can accommodate 1 molecule each of methane, ethane, and propane, and therefore the saturation capacity is precisely 4 molecules per unit cell. On the other hand, if we look at pentane, which is red circles, normal hexane, green squares, normal heptane, the hexagonal symbols here. We note that the saturation capacity is limited to 2 molecules per unit cell because NC5, NC6, and NC7 cannot be accommodated within a single segment and require 2 channel segments to accommodate each of these linear molecules. NC4 is a little bit of an exception because only at very high pressures can the NC4 molecule be made to occupy 1 channel segment each, and the isotherm shows a marked inflection point. Now, from the CBMC simulation data, we can determine the Henry coefficient for each of these molecules, and the Henry coefficients are plotted here as function of the carbon number of the n-alkane. The Henry coefficients are shown here on the left axis, shown by the red circles. So going from C1 to C2 to C3, we have an increasing values for the Henry coefficient. However, on increasing beyond C3, we see that the Henry coefficient decreases because the NC4 molecule is incommensurate with 1 channel segment, whereas C3 is precisely commensurate with the length of 1 channel segment. So this C3 molecule sits cosily within 1 channel segment, whereas NC4 is less cosily confined within the channel segment. And this is also true of NC5. This has a degree of incommensurateness. So the decrease in the Henry coefficient is a reflection of the incommensurate adsorption within the channel segment. If we increase the chain length further, we see that NC6 is again higher in value with regard to the Henry coefficient, and the value is the same as for C3. This is because NC6 is commensurate with 2 channel segments. In other words, a single NC6 molecule has a length that is commensurate with 2 channel segments. So this is again commensurate, and NC7 can also occupy 2 channel segments. Also plotted in this figure, with shown in these green squares, are the data for the diffusivities determined from molecular dynamic simulations. These diffusivities are determined at 0 loading. We see that the diffusivity data has a characteristic that is precisely the inverse of the characteristic of the Henry coefficient. In other words, if the adsorption characteristic is commensurate, then the corresponds to a lowest value of the diffusivity. If the packing is incommensurate, as is the case with NC5, its diffusivity is the highest. It's interesting that this is non-monotonic behavior is linked to the adsorption characteristics, and the phenomena of commensurate adsorption implies low diffusivity because the molecule is comfortably ensconced within the channel structure. If the adsorption is incommensurate, as is the case with NC5, the molecule seems out of place and therefore has a tendency to be more mobile. So incommensurateness implies a higher degree of mobility. Now, these are molecular simulation data. We have here experimental data for adsorption of 1 propanol and 1 butanol in cobalt formate. And we see that 1 propanol has a higher adsorption strength than 1 butanol. This is precisely analogous to the behavior of the n-alkanes as shown here based on CBMC simulations. Put another way, the experimental data serve to confirm the molecular simulation information. Further details on the data on adsorption and diffusion of normal alkanes in cobalt formate can be found in my publication noted here. Let's move on to adsorption of normal alkanes in MFI zeolite. MFI stands for mobile 5. MFI zeolite has a topology consisting of a set of intersecting channels. These are the straight channels. These are the zigzag channels in this direction. These are the channel intersections. There are 4 channel intersections per unit cell. The size of the channels is approximately 5.5 angstrom. The length of a normal hexane molecule is commensurate with the distance between 2 intersection sites. The normal heptane molecule, on the other hand, has a length that is slightly longer than the distance between 2 channel intersections. Here, the graph shows the unary isotherms for C1, C2, C3, C4, NC4. This is NC5, NC6, and NC7, where the loadings are expressed in the units of molecules per unit cell, and the x-axis is the bulk fluid phase fugacity with the units of pascals. Recall that there are 4 intersection sites per unit cell, and that the length of a normal hexane molecule is commensurate with the distance between 2 intersection points. Therefore, the saturation capacity of NC6 is precisely 8 molecules per unit cell. If we look at the saturation capacity for NC7, normal heptane, we note that the saturation capacity is lower than 8 molecules per unit cell because the length of a normal heptane molecule is slightly larger than the length between adjoining intersection points. We also note that the isotherm for NC7 has a strong inflection behavior, and the inflection occurs at a loading of 4 molecules per unit cell. Recall that there are 4 intersection sites per unit cell. Let us see how the adsorption characteristics of normal alkanes in MFI zeolite influence the diffusion or diffusivities of these gas molecules. The MD data for the diffusivities at zero loading are plotted here as a function of the chain length of the normal alkanes. We note that there is a minimum value for NC6 because the length of a normal hexane molecule is commensurate with the distance between the adjacent intersection sites. Normal hexane, normal heptane is incommensurate with the distance between adjacent intersection sites, and this incommensurate nature leads to a higher diffusivity value because normal heptane doesn't sit too comfortably within the intersecting channel structure of MFI zeolite. The minimum in the diffusivity for the normal hexane, as witnessed in the MD simulations, is also reflected in the experimental data of TALU presented here for 3 different temperatures. And we note clearly that there is a minimum value for NC6. Further background details are provided in my paper published in 2017. The quasi-elastic neutron scattering QENS data for the diffusivities of normal alkanes in LTA5A zeolite are plotted here as a function of the carbon number. The data shows a minimum value for NC8. The non-monotonic behavior in the variation of the diffusivity with increasing chain length has been termed the window effect. In order to rationalize this, I present here snapshots showing the conformations of NC8 within the cages of LTA5A zeolite. The corresponding snapshots for NC13 are shown here. If we examine this snapshot, we see that a single cage of LTA5A zeolite can accommodate 2 molecules of NC8. Indeed, the capacity of a single cage is commensurate with 2 molecule of NC8. With increasing chain length, it is no longer possible to accommodate 2 molecules per cage, as is exemplified here for the snapshots with NC13. We note here that the molecule is too long and a single molecule occupies or extends over 2 cages. Same thing here. So it is not possible to accommodate 2 NC13 molecules within a single cage of LTA5A. So NC13, the chain length is incommensurate with the cage capacity, and that explains the higher value of NC13, the diffusivity of NC13 with respect to the diffusivity of NC8. So the message once again is that if a molecule is comfortably accommodated within the framework and sits in a commensurate manner, then it has a low diffusivity or lower diffusivity as compared to another molecule which has incommensurate adsorption. Because if the molecule has a degree of a departure from commensurateness, it is not comfortable and prefers to move around, and this increases its mobility. So the message is, the more comfortable a molecule sits within the framework, the less mobile it is. And in the case of LTA5A zeolite, NC8 molecule undergoes less frequent intercage hopping than NC13 molecule. Let's move on to consider the adsorption of xylene isomers in AFI zeolite. AFI zeolite has a one-dimensional channel structure shown here. The distance here is 8.4 angstrom, and the distance here is 7.3 angstrom. Orthoxylene has a dimension shown here. It's a flat molecule, and the height of an orthoxylene molecule is such that it can be comfortably located at these grooves, and we have face-to-face stacking of orthoxylene within the AFI zeolite structure. Metaxylene and paraxylene, on the other hand, have dimensions that do not allow commensurate face-to-face stacking of as evidence in these two snapshots. The important result that ensues from these snapshots is that if we examine the unary isotherms, these are experimental data on the unary isotherms, the unary isotherm data for orthoxylene shows a significantly higher saturation capacity. The reason for this can be traced to commensurate face-to-face stacking of orthoxylene. A further consequence of these isotherms here is that mixture adsorption is selective to orthoxylene because of commensurate face-to-face stacking. Further details are available in this publication. MIL47 has lozenge-shaped channels of 8.5 angstrom in size, and the channel dimensions are such that it allows commensurate stacking of orthoxylene molecules. Metaxylene and paraxylene, on the other hand, cannot stack in a commensurate manner within the channels of MIL47. As a consequence, the experimental data of Finzi, published in Journal of American Chemical Society, 2008, shows that mixture adsorption is in favor of orthoxylene due to commensurate stacking of orthoxylene within the channels of MIL47. The justification for the commensurate stacking is provided in this publication in 2014. In contrast to MIL47, that has channel dimensions of 8.5 angstrom. Let's examine MAF X8, whose channel dimensions are larger, and this is a channel dimension of 10 angstrom, and the 10 angstrom channels are able to accommodate the paraxylene molecule because the height of a paraxylene molecule is commensurate with the channel dimensions, and this is also observable in this animation. We have commensurate face-to-face stacking of paraxylene within the 1D channels of MAF X8. As a consequence of this commensurate stacking of paraxylene, mixture adsorption of xylene isomers is selective to paraxylene, that is desirable in industrial practice. Further details are provided in this publication from 2014.